Hello, my name is Akmal Asraf. I am a PhD in chemistry, and today I am going to share some information about particle sizes. I hope you will find this video materials interesting and helpful. Here we go. Okay, particle size is one of the most significant pointers in industry, including pharmaceutical industry, in food industry, in cosmetics and other branches of industry. So this is one of the topics that we have to pay our special attention to. So what is particle size? Particle sizes refer to the diameter or dimensions of solid particles in all pharmaceutical materials. In reality, particles are rarely perfect spheres. They can be of different shapes. Here we can see different shapes of particles used in industry. And in rare cases, we can see this kind of spherical shapes, mainly in liposomes or micelles. Of course, we can see spherical shapes of metals, but the ores in organic salts might not have this kind of spherical pointers, spherical shapes, I mean. And these also have kind of impact on their property that might affect the drug formulations. That's why we need to understand particle size, particle shape, and some other properties of particles. We measure an equivalent diameter for the particle size, and for that, okay, diameter is used. We are going to talk about the diameter a bit later. Here we can see the methods for particle size analysis. The most common and classical method for particle size analysis is sieving. Here we can see that sieving can be carried out in several steps. The large ones and smaller ones can be held in upper layers, and the smallest particles can be gathered at the lowest level of the sieves. So by this kind of method, some powders can be analyzed. I mean, their mass and the percentage, the frequency can be analyzed by weighing the different sizes of the particles. And there are some pointers about the sieves that even if it is widely used in industry, and sometimes they need to be cleaned. The compound is, I mean, the particles can be stick in some cases. So they are required to be pure, kept pure. And the second method of particle size analysis is optical microscopy. In our previous lesson, we talked to you about optical microscopy. Optical microscopy is being used more and more in industry, in research, in science and education. Today, we have, I mean, universities and industries have up-to-date optical microscopes that enable us to see the shapes of inorganic materials and both and also the conformations of some fibers like cellulose or its derivatives. So this is another method to check the particle size. Okay, another method for particle size analysis is laser diffraction. Here we can see how it works, and laser diffraction can be used for both powders and for solutions. So different materials can be used for them. Different tools, different mechanisms can be used for different aggregators. And here we can see that the size of the material can be determined by the flow, by checking the size of the material to be flown upside down. Okay, this is the third method for particle size analysis. Another method is dynamic light scattering. Here we can see how it works. In such tools, okay, there is such a mechanism that the light is scattered from different sides. So based on the light scattered from different sides, the sizes of the particles inside the solution can be studied, checked, and automatically the particle sizes are determined. And this is one of the most, let's say, practical methods in research in laboratories in pharmaceutical industry. It is also used quite effectively. Uh, for liquids, okay, we can see, we can check the sizes from nanometers to large micrometers, a very high range of size that enable us to to utilize this tool effectively in research and in industry. Okay, another method is the last one is a sedimentation method. Uh, Shaking and rotation are utilized for sedimenting some for sedimentation of some particles with higher mass. As we see, as time goes by, the particles that have high mass are expected to be sedimented, to be gathered at the bottom of the, let's say, volume where the samples are inserted. So this is another method that can be utilized in industry. And now here by these photos, we can see the methods that are used to reduce the particle size. Particle reduction of particle size is a method that are required to be used in industry because the size of the materials are not let's say proper enough to be used in industry. Here we can see different milling tools. Here we can see a ball mill that utilize different balls to grind the materials. And here we can see hammer mill that utilize hammer-like structure to grind the size of particles. And here we can see jet mill, which is a little bit more updated system compared to these two tools that utilize only mechanical forces. Here we can see the usage of compressed grind air that is used to separate some micronized particles that could be separated from the system by the compressed air or gas. So this is another method that is used to reduce the particle size. not only to reduce but also to separate and filter some of the particles. And high pressure homogenization is also used to reduce the particle size, and spray drying is another method, the elements of which can be integrated with these methods. Okay, next. And now we are going to understand what the powder is, because in pharmaceutical industry, the most used materials are powders that are used in tablets, that are used in different drug formulations, capsules, in other forms. So powders are substances or mixtures holding fine and dry particles produced by grinding, crushing, and disintegrations. Powders are used in pharmaceutical industry, food industry, cosmetics, etc. The shapes of powders are repeated throughout the powder. Here we can see different types of powders that are used in pharmaceutical industry. And these kind of powders have, let's say, different shapes. And the shapes of these powders can be regular, can be irregular. Uh, Irregular shapes can be, let's say, more common. I mean, we can find more irregular shapes inside the powders, and the regular shapes can be different. They can be spheroid, they can be a spheroid structure. Some column-like structures can be found. Plate-like structures can be found. This kind of budding rosette structures can be found. Polycrystal structures, as shown here, can be found there, and small and big irregular shapes can also be found in the composition of the particles of the powders. And here we can see various shapes of powders as well, needle-like, rod-like, flake-like structures, angular particles, lamellar particles, and rounded particles, spherical particles, cylindric, cubic, equivalent particles, and rhombohedral particles. So different particles, different shapes can be found in different powders. That's why, okay, compared to X-ray crystals, powder crystals are more used to see the sizes of the particles. And next lesson, hopefully, we will learn about X-ray diffraction. And these are some other types of shapes that could be found in powders. And here we can see the structures of powders that are used in pharmaceutical industry. Here we can see the structure, microstructure of aspartame, which is used as sweetener. And here we can see the crystals of sodium chloride in a 2 micrometer size. And here we can see the A1 belongs to xylitol, which is also used as a sweetener. And this belongs to crospovidone, which is used as binder in tablets. And this belongs to the starch, polysaccharide consisted of beta 1 for alpha glycosidic bonds that could be cleaved in the human body. That starch is isolated from the rice and from the potato for industrial usage. So these are about the structures of powders that are used in pharmaceutical industry. And here we can see the sizes that could be calculated. That could be how could be calculated is explained here. And the first one is about the sizing spheres. Spheres, the easiest to measure, but the rarest case. Every parameter is related to the diameter. So for spheroid structures, the diameter can be easily found. But for irregular shapes, this might be a kind of issue. So the have been developed different approaches to find the diameters of the shapes. And here we can see different approaches. So as the diameters of the particles is established, so then the area can be calculated by using these these formulas, and more information you can find in the video lessons given in the learning zone prepared by Professor David Armitage. And this is about the equivalent diameters. With spheres are perfect, it would make sense to express all shapes in terms of equivalent spherical diameter. However, deciding that the diameter is can be difficult. Diameter can be difficult, and many alternatives are available depending on how the template is examined. The method can be roughly divided into 2D methods. Okay, here we can see the 2D method, not the 3D one. So then the particles is viewed from above and compared to a circle, and 3D methods where the space is obtained from indirect measurements. And also the volume of the particles can be first, let's say, found, and then based on the volume, the diameters of the particles can be calculated by using this kind of structures. Uh, but this approach can be a little bit, let's say, difficult in terms of calculating the number of particles and then finding the volume, and then turn to the diameter. So these are about the diameters that could be calculated. The area that could be calculated based on the diameter. Okay, next. And powders are usually hygroscopic. We have to pay a special attention to the level of hygroscopy of the powders because they differ by the hygroscopy level. Some powders can have the hygroscopy level lower than 20%, between 20 and 40% that are named slightly hygroscopic, and more than 60%, which is termed moderately hygroscopic. Between 40 and 60, yeah, I'm sorry. And if the hygroscopy level is more than 60%, we classify them as very hygroscopic. Let me remind that hygroscopy stands for the property to absorb water from the air. So based on these properties, okay, different levels of, let's say, purity and purity of the powders can be calculated as time goes by. That's why they are required to be kept and protected from the interaction with the air. And here we can see the appearance of one type of 12-hydroxystearic acid, and this is also on 12-hydroxystearic acid. They are from different sources. Even if they have the same time of production, by the appearance they can differ, but by comparison, these two photos, I wanted you to understand that this one has more water absorbed on it. As the time goes by, some salts might have this kind of appearance structure because of the high level of water in their composition. So we have to pay a special attention to their, let's say, appearance, if necessary. Okay, before the usage, they could be kept at some temperature to dehydrate the samples, unless they are stable to treatment in high temperature. So these are the pointers that the powders should be paid some special attention to. And here we can see the types of conventional and innovative drug formulations. We said that the powders are used for tablets, capsules, and some other types like syrups and some other types of drug formulations used in medical practice. And today we know many, I can say, tens of different innovative drug formulations, including nanoparticles, different nanoparticles, and quantum dots measure pore structures, lysosomes, liposomes, solid lipid nanoparticles, and micelles, polymeric nanoparticles, dendrimer structures, and others. Uh, Even if these innovative drug formulations have been studied for over 2 decades, still tablets are expected to be the main drug formulations that reached the medical practice. Uh, that's why, okay, we have to learn about the tablets and powders as more as possible. And why do we need to measure the particle size? This is a question that we need to reach the essence. Why do we need to measure the particle size? Let's imagine, okay, the drug formulations have this kind of, let's say, particle size and small particle size, big particle size and small. If the particle size are small and the concentration is, let's say, high enough, we can expect some positive outcomes on the skin. For example, here the samples about the topical usage on the skin. And if the concentration is smaller, but the particle size is proper, so we can expect some positive outcomes as well as described here. But if the concentrations is high, but the particle size is big, so we cannot expect some kind of drug penetration through the skin uh, and some positive outcomes. I mean, if the particle size is big enough, they are expected to be on the surface of the skin, so we may not expect some effects of the drugs. And if the concentration is low and the particle size is big, okay, the efficacy of the drug lowers sharply. So these are the pointers to understand that the particle size is one of the most important pointers of the drug formulations to be effective. And here we can see another example to the question, why do we need to measure the particle size? Let's say we have one tablet, and as time goes by, that drug formulation starts releasing the active pharmaceutical ingredients. And as time goes by, we can expect the linear, let's say, release of the drug, and we can expect, therefore, some linear efficacy of the drug. Uh, But let's say if the drugs were not spread in the sample uniformly, let's say here in some part, in half of the tablet, the drugs may not distributed evenly, so we may not see the linear drug release here in this part, and there could be kind of enhancing and increasing and reducing amount of the drug release, so we may not control linear drug release, and then we may not expect linear efficacy of the drugs. So from this point of view, drug, I mean, linear drug release resulting from the linear I mean, drug, evenly distributed drugs in the tablet is an important point. And in this example, we can understand this point more comprehensively. Let's say we have two drugs A and B, and this color belongs to A, this color belongs to B. If they are distributed in the tablet evenly like this, and so we can expect the additive effect or synergistic effect of the drugs A and B. But if they are not evenly distributed, like here, let's say here there is no drug B, and here there is no drug A, and here there is no drug B. So when this part of the tablet releases drugs, we may not expect additive effect or synergistic effect of drug A and B. Therefore, okay, when the drugs are used in combination, we have to be able to provide similar, even distribution of all ingredients throughout the powder. And here we can see the significance of obtaining uniform mixtures. If we have ingredient A, ingredient B, ingredient C, or 1, 2, 3, we need to obtain the mixtures by blending. When we obtain homogeneous blending, so then they can be mixed with the fillers or binders of the tablet, and mixing them at the same time with the fillers and tablets may not be effective enough. So it could be better for us to obtain the mixtures of ingredients 1, 2, and 3, active pharmaceutical ingredients, and then obtain the mixture of these ingredients with the fillers and binders. So this is another point that deserves special attention. And this is about the factors affecting powder flow. Powder flow is the ability of granular materials to move, deform, and flow under gravity or applied force, defined as the relative motion of particles amongst themselves or against container surface. It is a critical, complex, and non-intrinsic property influenced by particle shape, size, moisture, cohesion, crucial for optimizing industrial manufacturing. So the size and shape of the particles of powder is one of the parameters that affect the flow of the powder. So if the flow, okay, is very, let's say, high, we can have some conclusion. And the factors that affect the powder flow are given here, and the ones related to particle properties can be, okay, their composition, density, particle size, shape, and roughness, surface friction, particle compressibility, moisture, electrical properties, and electrical properties is one of the significant pointers. Okay, compared to van der Waals forces, electrical properties might have hundreds of times, let's say, more attraction that could affect the powder flow property. And the powder properties that affect the powder flow are given here, including size distribution, bulk density, homogeneity, attrition level, power, compressibility, cohesiveness, coefficient of internal friction, coefficient of wall frictions, and others. And intrinsic factors can be temperature, air, humidity, compaction level, coating, segregation, anti-caking agents, and extrinsic factors include feeding rate, vibration, Hopper dimension, and design, discharge, and others. So there are many factors that might affect the powder flow. And here we can understand the significance of powder flow in the powder, free flowing property of powders. Here we can see and compare uh, the differences in the free flowing powders as given here and here in the example of sugars and cohesive powders that are given here and here in the examples of sugar and flours. So free-flowing powders have large, coarse particles with no forces between them. They are of granulated structures and they mix easily and segregate easily. And cohesive powders have small particles, fine particles with large forces between them. Icing sugar and flour can be examples for them. These are more difficult to handle and mix, but do not segregate easily once mixed. These are the pointers that worth special attention. Okay, now this is about the particle size and surface area. uh, Reducing particle size always increases the surface area. We can understand in this example. Okay, here we have this kind of cubic structure, and 1/8 part of this cube, as shown here, have three sides. When we divide this cube into eight smaller units, that we can understand that the surface of the particle doubles. So the property uh, to interact, to have physical interactions with other compounds of the tablet increases. So we can expect significantly differences in the powder flow and other rheological properties of the powder uh, based on the sizes of the particles. So reducing particle size always increases the surface area and therefore affects mass transfer, absorption, physical interactions, bioavailability, and we are going to understand the bioavailability a bit later, and absorption and the use of carrier particles. Here we can see an example that as the particle size is big, it may irritate skin, mucose, and if the particle size is about 2.5 milliliter, micrometer, if it's micrometer size, still it cannot enter the systemic circulation but reaches peripheral airway. When the sizes of the powders are nanometer size, as shown here, 100 nanometer. So we can expect they can enter the systemic circulation. And another point we have to pay special attention to is the total surface area per mass here. Let's say 1. But when it is divided into this kind of smaller particles, again, it can be 4 times greater when divided into this kind of particles. Again, it can be the total surface can be 100 times greater, and surface area even a surface area per particle is smaller, but the total surface increases. And as we said here, uh, higher surface area enhances affects mass transfer, absorption, physical interaction, bioavailability. Yeah, we can claim that enhances absorption, physical interactions, and bioavailability as well. So viscous liquids and very fine particles can be stabilized by absorption onto inert particles, rather like a sponge, which can be released when needed in the body. And if a carrier powder is in the form of fine particles, as shown here, or even smaller, rather than the coarse ones, there's a greater availability area per kg for absorbing an active ingredient. Since the surface of the powder particles increases, the property of absorbing active ingredients will be higher. So this is about absorption and the use of carrier particles. And here we can see the continuation of this property. Both the activation energy and rate of reaction can be increased when the particles have greater surface area per kilogram are used. Here we can see the enhanced physical interactions between the green compound and red compounds. Here we can see that red compounds can have physical interactions with the green particles by its surface only, and as it is divided into smaller particles, here we can see that the surface will be higher, so the interactions between A and B, red and green particles will be more and faster. And this is about the bioavailability and surface area. Uh, let's just first read the definition of bioavailability. It is the proportion of a drug or other substances which enters the circulation when introduced into the body and so is able to have an active effect, which means the bioavailability can never equal the total amount of the drugs administered by different routes. So the bioavailability of the drug is the one that enters the circulation. And these are the properties that affects the bioavailability. Uh, it can be molecular size, it can be solubility, it can be lipophilicity. Hopefully, we will learn the significance of solubility and lipophilicity in the future. And transport, they can be affected by transporting means. And solid carrier family transporters affected active transports, passive diffusion, and some others linked with metabolic stability. So a large surface area to mass ratio ensures that encapsulated drugs can be released more readily. Small particles can be absorbed more easily and influences drug potency, but it does not mean that we have to obtain the smallest size of the particles. The optimum size should be, let's say, uh, established, and the rate of release in so potency can be controlled by changing the particle size. The point that we have to pay special attention to is a large surface area to mass ratio ensures that encapsulated drugs can be released more readily, but their absorption is not high enough. So small particles can be absorbed more easily and influences drug potency. And this is about the particle size and route of administration. Okay, for different drug formulations, the particle sizes can be different. This is, let's say, a normal practice. And as shown here for a lymphatic route, reticular endothelial system, the particle size can be between 10 and 15 nanometers, the smallest possible size among the drug formulations. And the ones for long circulating carriers intended for brain and tumor, the size is expected not exceeding 200 nanometers. And for transdermal forms of drugs. Okay, it can be up to 600 nanometers, and for intravenous and intramuscular uh, administration, okay, the sizes can be between 200 and 2000 nanometers. For ocular utilization, it can be up to 3 micrometers. And the aerosols and intranasal drug formulations can have micro-sized particles. Okay, it can be up to 10 and up to 20 micrometers for aerosols and intranasal formulations, respectively. Grittiness, which means coarse sized, is unpleasant in mouth or on skin. And large particles may be trapped in diseased skin scales and could cause over medication. And large particles are dangerous when administered intravenously and given to eye. So these are the pointers that are taken into account. And this is about the sizes of intranasal administration. Intranasal administrations can be used against Alzheimer disease, Parkinson disease, epilepsy, schizophrenia, depression, and the sizes of the particles can be up to 80 microns, 80 micrometers, and in other case, the particle size were between 20 and 50 micrometers. And for microemulsion droplets, it was lower than 200 nanometers. So if it is smaller, let's say the penetration through the skin epithelial will be easier. If it's bigger, the stability will be smaller, but if they are used for intranasal administration, so we can claim the bigger sized particles can be distracted more easily, so the effects can be, let's say, high, can be better compared to the small sized particles. But info, this is the property that should be discussed in more details. Okay. And this is about the effective particle size on phytochemical composition and antioxidant properties of plant materials, ethanol extract. We cannot claim that the smallest particles can be expected the best to obtain the extracts that we want to have. I mean, for example, this size higher than 40 micrometers, smaller than 100 micrometers, can be optimum for obtaining ethanol extract that might, let's say, extract some polyphenols, for example. So this size may not yield high, let's say, efficacy. I mean, the concentration of the drugs may not be high enough, and in this case, okay, we might expect higher amount of compounds other than polyphenols, and this can be optimum. And if it is smaller, okay, the concentration of polyphenols can be low, and the concentration of some other particles can be high because of the smaller size. So so the sizes of plant or animal raw materials are also very significant to obtain some extracts from these sources. And this is about the significance of the liposons that are used as anti-cancer drug delivery systems. Here we can see the TEM structures, one slice of the liposons. What we have to understand from these photos, okay, this is at pH 7.4 and here at pH 6. In different pH, we can expect different shapes of the particles. I mean, the sizes of the particles, let's say. Shapes also differ a little. Okay. But here we can see at 6.4, we can see that the uniformity of the particles is not narrow enough as here. I mean, here the difference in the particle sizes is not as big as shown here, up to my understanding. I mean, for example, the size of this particle and these smalls is quite big, but here we do not see that kind of big differences. So this is about the effect of the pH on the same composition as shown here. And here we can see this similar claims. I mean, the effects of pH is shown here. And here we can see the differences by comparing the chemical compositions. And here we can also see the effects of pH on the particle sizes of liposomes. And this is the mixed with model liposome. And here we can see that the liposomes were gathered in these examples. So there are many factors that might affect the sizes of different drug formulations. And in the example of liposomes, we see that the pH might affect it and the composition might affect the sizes of the liposomes. And this is the SEM, scanning electron microscopy image of liposomes. We see this photo was taken from the paper entitled Enhancement of the Stability and Cytotoxicity of the Brain by Liposome Nanocarriers for Gastric Cancer Treatment and its application in gummy candy. We can make a conclusion from this photo that the size of the liposomes are very uniform, very uniform. We can see maximum 3 times differences between the liposomal structures. Let's say this one and this two one. Okay, they can be maximum, let's say, 5 times greater compared to each other. But in the previous one, we see that big differences were obtained. Maybe 10 times difference were seen here. And we can claim that these liposomes were more uniform compared to these ones. Okay, and this page is about the influence of dry grinding on physical, chemical, and surface properties of talc, which is used as fillers in producing tablets. And here we can see the effects of grinding period of specific surface area, pore volume, color, and oil absorptions of talc. As surface area, as we see here, doubled from 10 to 19. Pore volume also almost, let's say, doubled from 4.2 until 7.6. And oil absorption capacity also increased linearly, which means, okay, the surface area of the particles increase, so the absorption also increases, and that also does not change the color of the particles significantly. So these are the points that we should try to understand. Okay, next. Okay, these are all. I hope you will have much information from this video lesson. And if you have some difficulty, I recommend you to watch these video materials again. And I express my thanks for your time spent for it. Bye-bye.